Hi all, welcome back to my channel on ozone technology course. This will be session 22B on cooling tower system fundamentals. It will continue with the mechanism of corrosions. The subject I'm going to deal with in this session will be what is bacterial corrosion and its minimization, what is erosion corrosion and its minimization, and what is electrolytic corrosion and its minimization, and what is chemical corrosion and its minimization. First, we look into the definition of corrosion. Corrosion is a process where metals are oxidized to an oxide combined with moisture and eventually to possibly soluble halides, where in the presence of electrolytes. Corrosion weakens the metal, forms holes, and breaks down the metal. However, please note, metals can form metal oxides, which normally are very stable and can be used as passivators, protecting the metals from further corrosion with oxygen. The issue with metal oxides and metals is more a reaction in the acid medium to form chlorides or halides. The good examples of iron passivators are strong sodium hydroxide, sodium chromate, and ozone. For example, if you treat an iron with very strong sodium hydroxide, maybe 1% or 2% or so and above, the iron metal gets passivated, so much so that even acids will not react with it. So it becomes very, very strong and resistant to all substances, including acids. Likewise, before 1984s or 1985s, sodium chromate was being used, or dichromates were being used as preservators or rust prevention or corrosion resistant chemicals in cooling towers. Now, because of the fact that chromium that goes into the seawater has a very bad effect on the marine life, sodium chromide or any components of chromium are banned from being used in cooling towers. Ozone has the same property. In fact, that what will happen is ozone will react to your metals to form metal oxides, and as you know, metal oxides are very resistant to further oxidation. Irrespective of how the metal is passivated, it is not protected from galvanic and electrolytic corrosion. Ozone does form a metal oxide coating to protect the corrosion from oxygen. But if electrolytes are present, corrosion cannot be prevented. Please note this information, which is extremely important when you start dealing with corrosion of metals and people complaining that such and such a thing causes corrosion. They'll have to understand how corrosion actually is formed or occurs, and steps must be taken how to prevent them. One type of corrosion is called the erosion corrosion. This is, you all will realize that water rushes through the pipes at very high speeds. The suspended particles that are in the water exert as missiles, which hit the surfaces and bends of the metals, causing pitted corrosions over time. The pits are generalized and not congregated. The suspended particles can be insoluble calcium carbonate from scales, dirt, dust, silica particles, or sand particles, etc. The maximum impact of erosion corrosion is at the bends, caused by the continual collision of the particles onto the pipe surface as the water flows through. You might recall corrosion occurs in the river, and as the river flows and winds, every time it makes its turn, it hits the bend, and slowly a new tributary is found. The other type of corrosion is corrosion by chemicals. Many chemicals can react with metals and break them down. For example, hydrochloric acid, all the acids, they react with the metals to form chlorides. So when there is a reduction in pH, it will be an acid surrounds, and metals will react with the acids to form metal chlorides, and eventually the metal gets corroded. The main objective of water treatment must be to have low bacteria, which cannot be eliminated as it is in an open system. There should be no biofilm, because biofilm is the one that provides, that sticks to the sides of the pipes, which is a very slippery surface, which is called the biofilm. That is actually the growth of bacteria on the surface. Biofilm, of course, will activate the formation of scales, because when the water concentrates and becomes very saturated, crystallization of the calcium carbonate occurs, and the biofilm will exert as a crystal around which the scales form. A continuous layer of scales that form will eventually narrow or restrict the pipe, causes increasing resistance to the flow of water, causes increase in pressure of the system, and reduces the heat transmission within the heat exchanger. This picture in this slide shows a picture of a pipe bend, and you will be able to see the various pits and holes at the turning point, where the particles hits the surface of the pipes. If you look into this diagram, you find that in A, there's a small dent is formed, and then as the water flows with the particles, it hits further. There is an eddy current which continues hitting it. Eventually, the pit becomes deep and deeper and deeper until pitting holes are formed, and that is how the pipes start leaking. Another form of corrosion is called biological corrosion or biocorrosion. There are two types of bacteria generally that causes the corrosion. One is the iron bacteria. The iron bacteria actually releases acids and dissolves the metal and utilizes the metal for metabolism of the bacteria. By the releasing of this acid and dissolving the metal, the bacteria causes holes. So wherever the bacteria is accumulated in little spots. These spots will have little holes or pitted holes. Eventually, that may go through into the pipe and leak. The pipe will leak. With respect to the sulfur bacteria, what it does is it uses the sulfates in the water to oxidize and uses for metabolize and for the metabolism. What happens is once it takes such sulfate and uses it as a food, what is resultant is hydrogen sulfide, which will be oxidized to sulfuric acid generally, and which will then start corroding your pipes. This also causes pitted corrosion. That is, wherever there are bacterial colonies, each different colony will have a concentration of the acids, and there will be a pitted hole, and finally a big hole that water can pass through under the pressure. Please note that in both these cases, bacteria has to depend on the slime. The slime is actually all the total dissolved organic matter which eventually settle on the side of the pipe and cause a slime, and bacteria will use the slime as food and consolidate their colony. The ideal situation will be is to ensure that no slime is formed, so that the bacteria has got no opportunity of sticking onto the biofilm or slime and forming colonies. So if there is no biofilm, then the bacteria will not consolidate, and therefore there will be no corrosion. This slide gives you a bit more information on the biocorrosion. The type of bacteria that is called sulfur-reducing bacteria, the name is D-sulfovibrio, D-sulfotomaculum, or D-sulfomonas species. These are the two types of species that metabolize sulfur. Please note the names may appear to be very complicated, but if you translate it, it is D-sulfo. That means using sulfur. Vibrio. Vibrio is the shape of the bacteria. D-sulfotomaculum is obviously using sulfoto oxidizing maculum, and the other one is like Pseudomonas, D-sulfomonas species. The iron-reducing bacteria, this is Gallionella ferrugine or Ferrobacillus species. If you notice, ferrugine is to do with iron, Ferrobacillus is a bacillus type, and bacillus is little needle-like appearance, and ferro is iron, and this produces acid. Other acid-producing bacteria are Pseudomonas, Aerobacter, Bacillus, and sulfur-oxidizing bacteria, Thiobacillus, which I have is part of the sulfate-reducing bacteria. Now, iron-reducing bacteria means iron is being used. When the bacteria needs iron to metabolize, it produces acid, dissolves the iron of the pipe, and then uses it for its metabolism. If you look at this is the wall of the pipe, And as the water goes in, you find that at this point in the slime, bacteria accumulate, and then they do all their work. They generate acid. The acid will cause electrolytic corrosion. And it may be anaerobic. When it is anaerobic, hydrogen sulfide is formed. Hydrogen sulfide then reacts to form sulfuric acid. The same thing occurs if it is a sulfate reducing bacteria. As the water flows, the corrosion eventually, as the corrosion continues, eventually reaches the outside of the pipe, and because of the pressure, it will start leaking. These are the layers of scales. What happens is you have a first slime layer which contains a lot of bacteria. Then the scales deposit on it and reinforces it as hard, but it is porous. Then you have the second layer of slime is formed, which also then gets scaled up to a hard surface, yet porous, and then the third layer, and so on. No matter how many layers you have, you will note that bacteria can move in and out through the porous surfaces. So they are quite happy, they reside here happily, and where you use chemical treatment to try to get rid of the bacteria, some of the bacteria at this part, right at the bottom, may not even be exposed to the chlorine, for example, or biocide, for example, and therefore they will continue operating or living while only the surface bacteria gets killed. So as soon as the chlorine or antiseptic or disinfectant is removed, these bacteria will come out and consolidate the rest of the areas. So bacterial corrosion is very serious. So it is very important that when you look after the cooling towers, you try to have as low bacteria as possible, because eventually you still will get corrosion by the bacteria. The pictures in this slide shows how the corrosion will look like. If you would notice all the parts at which that is corroded, this is the header of the chiller plate, and you see the little big holes are the holes of the pipes through which water flows for cooling, and the copper is corroded to copper sulfate, the blue color. So you find that a lot of corrosion takes place. Holes also occurs in the copper tubing, and it will start mixing up with the air conditioning liquid which flows within the copper tubing. Here is more a blown out picture of the side of your pipes. You find that wherever the bacteria has accumulated, the acids generated will cause holes, and the holes will resemble the pits of pitted corrosion. Thank you for watching my video. We've come to the end of this session 23A. Please proceed to session 23B, which will continue with mechanism of corrosion in cooling towers. If you are new to this channel, please refer to sessions 1 and 2 that will explain the course program, and 3 to 23 for the sessions in detail of the program. If you like the course, please click the like icon and subscribe icon, when you will be notified as soon as further sessions are released and uploaded. Thank you.